Hey, what's up, everybody? I am going to try to keep this as short and succinct as I possibly can, but, we'll see how that ends up working out for me. Alright, so the first thing that I think I need to say is I just need to wrap up the discussion we were having last time, so I'll just say this. There's a few ideas that you need for the homework, and I mean, I think you probably would figure this out for yourself, but I should talk about it. So this is back to work and energy, right? So the two things I need to do are define the idea of power, and then also talk about how to analyze like a force versus displacement graph, because you need to be able to do those things for the homework. Okay, so let me just say that power is the rate at which work is done, or we could also say the rate at which energy is being expended. Okay. So we could define this to be something like this. We'll use a capital P, and we define this to be just some amount of work over some time interval. All right. And I mean, this is it. This is pretty much it. Okay. It's it is a scalar, right? Work is a scalar, energy is a scalar, so this is also a scalar. So we could say like the total power in a given situation is just the algebraic sum of all the individual powers, right? So I can say something like, if I want to say P total, right? If you imagine like several different forces doing work on an object over some distance, then I could say that the total power in that situation is just the sum of all the individual powers. So it's just like P1 plus P2 plus dot 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 all the way down to the nth power. Okay. So there is like one other equation involving power that is useful to see, and I think you also kind of need this for the homework. So let me just expand this here. Okay. No, I'm not gonna do it. Sorry. I'll just say this. So let's just talk about again like one of these powers. Let's just say you have maybe you have multiple forces doing work on an object, and you're asked about the power of like one of those forces, or the power associated with the work being done by one of those forces, right? So if you look at the equation that I wrote, it would just be the work associated with that force over the appropriate time interval. Okay, but let's remember that work is a force times a displacement times a cosine of theta. It's still over a time interval. And I'm going to write this in a different way. I'm going to write Fi d over delta t times cosine theta. Okay, and this is just inside the parentheses here, right? This is just a displacement over time, and that's what we would call a velocity, right? So we could say something like this. We could say that the power in this situation is just the force times speed times cosine theta. Now you should understand that this only works for a constant force and a constant speed. Okay, so just be mindful of that fact, because that was kind of baked into this into this quick derivation that I did here. All right, so I think these are the only two equations with power that you need. You just need to know what it is, and then this one particular form of the power equation for like a given force with constant speed. Okay, I should also tell you the units, right? So let's just say the units of power are those of energy over time, right? So this is called a watt. This is called a watt, and 1 watt equals 1 joule per second. Pretty straightforward, I think, right? We use a capital W for watt, and we already know what a joule is. I hope everybody knows what a second is, and that's it. Okay, so let's also talk very briefly about, and I'm not even really going to probably write anything down here, but I just want to show you something. For one of the homework problems, you kind of have a situation like this. Now, obviously, the plot is different, but what you need to do is you need to figure out, like, how to calculate the work done on an object by a, by looking at a graph. And so, in this situation, the work done is just going to be the area under the curve. Okay, so let's just assume that this displacement is in meters and this force is in newtons. What I'm going to say is that the area under the curve between 0 meters and 5 meters is positive, right? This is just a math convention that we also use in physics for situations like this. So the work being done in that situation is positive, right? So what I'm saying is the area under the curve is above the horizontal axis for the first 5 meters here. We associate that with positive work, okay? Then from 5 to 7 seconds, not seconds, meters, 5 to 7 meters. I'm already thinking about impulse and momentum. From 5 to 7 meters, the area under the curve is negative, which means that the work being done from 5 meters to 7 meters is negative, okay? And you can probably just look at this and see that in this situation, if you want to think about the net work, right, being done on this object, whatever it might be, there's more positive area than there is negative area, so that is just going to be a net positive for the work being done, right? And you can calculate areas under curves using integrals and whatnot, but we're not supposed to do that in this class. I mean, we're not going to do that in this class. But you can also just kind of do a geometric analysis. Like if I wanted to figure out the area under this curve, I would note that like here there's kind of a rectangle, right? So I would just figure out what the area of that is. Here is a right triangle, so I can also just do like 1/2 base times height, figure out that area. I mean, this part right here between 5 meters and 6 meters is just half. We can clearly see that it's just half a square, right? And the area of one of these should be like 1 Newton meter, so this would be like negative. You have to remember that it's under the curve, right? So this would be like a negative 1/2 Newton meter, or a joule, I guess, right? And then over here you just have 1 square, right? So hopefully you kind of see how you're supposed to go about this. And actually, you know what? There's actually a better diagram I'm just seeing right here. So let me just show this to you very fast. So it's a little bit smaller, right? But this is kind of communicating what I was trying to say, which is that like you look at this and you think, okay, there's a rectangle, there's a right triangle, there's another right triangle, there's another square, rectangle, whatever, right? And you just have to remember that when you're above the curve, the area is taken to be positive. When you're above the horizontal axis, the area is taken to be positive. When you're below the horizontal axis, right, the displacement axis, the area is taken to be negative. Just say that one more time. The area under the curve is what we want to calculate. But when you're above the horizontal axis, that's taken to be positive, and when you're below, it's taken to be negative, okay? So you'll have to, fight with that problem a little bit, I assume, because it's kind of obnoxious, but I think everybody can do it. All right, now we're going to move on to the new stuff, right? So I need to talk about the impulse momentum theorem. Okay, so what we're going to do here is we're just going to look at Newton's second law, right? So I'm going to say, recall that Newton's second law says something like this. It says the net force on an object is equal to the mass times the acceleration on it. And let's, think about a one-dimensional situation right here, and I'll just explain to you how this generalizes to, 2 or 3 dimensions. But let's just imagine all this is happening along the horizontal axis right now. So, I'm not going to write vectors or anything like that just yet. What you should, note is that this is actually just, for the acceleration, right, it's just a change in velocity over a change in time, right? This is something that we discussed, maybe week 1 or week 2 when we talked about kinematics, and it's true, and hopefully you all remember this, but it is just a change in velocity over changing time. All right, so what we can do is we can rearrange this a little bit. I'm going to do a few things here. I'm going to multiply both sides by delta t. So on the left-hand side here, we have f net times delta t. And on the right-hand side, I'm going to write this delta v as v final minus v initial. Okay, so I don't think anything, there's nothing really too shocking about what I've done here. Just a little bit of algebra and thinking back to 1D kinematics. Okay, so then the last thing that I'll do is I'll just say that this is going to turn into f net times delta t is equal to mv minus mv naught. Okay. So I'll say this, the left-hand side of this equation. So when I say the left-hand side of the equation, I'm talking about the very last equation, right, where I arrived at the result that I wanted. And the left-hand side of this equation is called the impulse, and the right-hand side is called the change in momentum. Okay, and I know we haven't defined momentum yet, but I'm just telling you some of the words, the verbiage here for this equation that we've got. Okay, so yeah, impulse and momentum, right? That was the topic for today. That is the topic for today. So this kind of suggests that momentum is just this quantity of a mass times a velocity, right? So in 3 dimensions, or let's just say in okay, this shouldn't be too hard. Let's just say in higher dimensions. Sorry, that's fine, I think. Momentum is defined to be m times v, and these are momentum is a vector, and so it is v, right? So what we have here is we have this thing p, right? We're going to use lowercase p for the momentum. Sometimes an uppercase p is used too, but it doesn't really matter. Left-hand side is called the momentum. On the right-hand side, we have a mass times a velocity, right? So the velocity is a vector, which is why momentum is a vector, and the mass is just a scalar, right? It just sort of changes the magnitude of the velocity vector and gives us the momentum. Okay, so another way of saying this is an object, let's just say a massive object, and by massive I just mean it has mass. It's not negligibly massive, of mass m moving with some velocity v, has some non-zero momentum p. Okay, so this is just a definition, and it's a useful one. Momentum is a pretty important idea, right? Actually, for our purposes in this class, if I know, say, the mass of an object, it's, well, let me say this. If I know, an object, okay, third time's the charm. If I know the position and momentum of an object, I basically know everything about it, right? We haven't talked about some of the ideas that go along with this yet. We will get to them, but so it's pretty important to understand momentum, and it's usually a big topic in a class like this, any physics class, really. Okay, so we've defined this thing. It's a vector, right? Called momentum. We'll talk about the units very fast. That's easy. So it must have units of mass times velocity. So its units are, and this is going to be kilogram meters per second in SI, right? These are the SI units. Of course, we could have any number of different ways of expressing this. But we'll stick with kilogram meters per second, and there's no, there's no shorthand for this. There's no, remember we called like a joule a Newton meter, or rather the other way around. We called a Newton meter a joule. So we could always write Newton meters, or we could write joules. In this case, there's nothing to write other than kilogram meters per second. Okay. So it's got those units. It's a vector. Now, let's just talk about the left-hand side of the equation that we got, right? So on the left-hand side, as mentioned above, I like that, we have the impulse. So let's define this to be, so this is a vector, right? And I'll just call it I think sometimes J is used. I don't know why. I understand why we don't want to use I, because we use I later on for like moments of inertia, but we're kind of running out of symbols here. So let's just say that this is our impulse. And it's a vector, right? Because for the equation that I wrote, right, that was one-dimensional, but I'm telling you that this generalizes to multiple dimensions. And so if we have a vector quantity on the right-hand side, we must also have a vector quantity on the left-hand side. And this is just, what it is. It's the impulse. So you could think about how maybe this works in real life. If you, for instance, like if you apply a force to some object over a period of time, that is going to cause the object's momentum to change, right? Because we understand that applying a force to an object makes it accelerate, given the right circumstances, and obviously acceleration brings with it a change in velocity, and this gives us then a change in momentum, right? So I mean, like, this is, maybe this seems like a bunch of technobabble, but like, I think we all understand that if you just apply a force to an object over some time interval, you impart some speed and therefore momentum to that object. Okay, so don't get too freaked out if this sounds very theoretical and confusing, because it's actually very practical. All right. So okay, so we've defined momentum, we've defined impulse. Now, I mean, I could talk about the units of impulse, but I think we all probably see that it's Newton seconds, right? Because we have a force times a time. But it also must be the same dimensions as momentum, right? So it does also work out to be kilogram meters per second, all right? I want you guys to think about units, and I am largely happy with seeing you at least try to write the units. So let's just all work to keep me happy, because that's what this is about, really, right? It's about me staying happy. That's pretty much the only thing that matters here. You probably don't agree, but that's okay. So yeah, just keep being good about the units and at least trying to write them, and everything should be fine. Okay. Let's see here. We should also talk about conservation of momentum. Okay. And then I'll spend a little bit of time looking at some simple problems. But I just want to give you kind of the bare minimum of the theory here before we do that. So I will just say something like, we can consider the total momentum of a system of particles or masses, right? So in this situation, if we have, say, multiple objects moving around, right, multiple massive objects moving around with different velocity vectors, we can think about the total momentum here. And I'll just call this like P tot for now. And this is simply going to be the vector sum of all the individual momenta. I think momenta is the proper plural of momentum. I actually took Latin in like middle school. I don't really remember a damn thing, but they seem to think it was a good idea to teach us that. So anyway, this is what we can write. We can just say that, say we have n masses moving around, right, and each one maybe has a different, velocity vector. The total momentum of the system is simply the vector sum of all the individual momenta. okay? And, you know, so if you had, say, like, three masses, one's moving to the right at some speed, the other's moving up with some speed, and the other is like moving diagonally down with some speed. You know, you just write out each one of their masses times their velocity vector, and that's it, right? So I'll just show you what this looks like, maybe just to be thorough here. So I'm going to say let's say m1 times vx1 vy1, right, plus m2 vx2 vy2, right, and so on all the way down to the last, let's say mn times vx and vy n. Okay, so this is what this looks like, right? This is what it will actually look like when you're, you know, trying to calculate the total momentum of a system of masses. And it's just, you know, it's almost kind of tedious, right? Because you just have to write each mass times its velocity vector. But it is a useful quantity, as I said. Okay, so the total momentum of a system of masses. And so the other thing maybe to note is that in the absence of external forces, momentum is conserved. So maybe what this means is I can write something like, thus I can write that the initial momentum equals the final momentum. Or maybe P equals P prime or something, right? If you want to use the prime notation, this is also commonly used. Sometimes using a lot of subscripts can get kind of unwieldy. So we're just going to say that in the absence of external forces, the momentum is conserved for a system of masses. So this is, you know, a pretty important statement, and we'll do a lot of problem solving with this idea. Okay. So, you know, this is a natural thing to think about here as a collision, right? So maybe, I mean, this is gruesome, but I'll just say it. Like, if you've ever seen a car crash, let me put some words, right? If you've ever seen a car crash, you know, sometimes the bodies of the cars get so mangled that they stick together and move as one object after the collision, right? And this is something, this is a situation we might try to apply conservation of momentum to. You know, I mean, there's other, like, a lot of these examples are kind of necessarily violent, right? Like shooting a gun at a block, or, you know, a bullet hitting a block, cars colliding. You know, like a one football player tackling another, right? I mean, it's a violent world we live in, okay? But you know, that's not my fault. So hopefully that's okay. But you know, and I don't want to make light of the idea of you know, an automobile accident or something like this. But this is a good example to think about, because you know, what we have in this situation is a very natural kind of example of conservation of momentum. All right, so we could talk about what happens in maybe the 1D case like this, right? Like, let's say, you know, consider two objects moving along the horizontal direction, one of mass m, and the other of mass big M. Let's say little m moves to the right with speed u, and maybe big M moves to the left with speed v. So I'm going to also probably use, you know, u for a symbol in lots of these problems, right? I'm not going to do a ton of problems in this video, but like if you come to office hours or I'm doing a review session, I will also use you just because I don't like to write a lot of subscripts, and I think that this does simplify things a bit. And so if they collide and stick together after the collision, conservation of momentum in this situation looks like this maybe, right? So I'll just write these as, I won't bother with the vector symbols because it's one-dimensional, right? But you should understand again that momentum is a vector, so it's a very important idea. And if you know nothing else about momentum, you should know that it's a vector. So what would the initial momentum be in this situation? We have, let's say, the momentum of the smaller mass, and I say that it's moving to the right with speed u, so I'll just write mu. And then for the bigger mass, it's going to be big M, and then I'm going to put negative v here, because even though we're talking about one dimension, we still have to put the appropriate plus or minus signs to indicate the direction of motion, okay? So we'll just write this. And this is going to equal the final momentum, right? And what we're going to say is we're going to say that they stick together and move as one object. Maybe their bodies get sort of deformed a little bit, and this is what permits this. And I'll just call this finer of. Well, I'm really having trouble with words today. I'll call this final speed that they move at, or this final velocity, big V. And so we could figure out what this is, right? We could figure out what big V is. It's not too terribly difficult, I think. And so we could just say something like this. We could say that big V is therefore going to be mu minus big M little v over big M plus little m. Okay, so this is where two objects collide and they stick together and move as one object. Now there is a word for this, and I can never remember what it is. I think it's, I won't say it, just give me a second while I confirm this. Look, I don't remember the words. I know how to do the problems and stuff, all right? So, don't judge me. But, sometimes this vocabulary gets a little annoying. Okay, so this is called, let's say that this is a perfectly inelastic collision. Okay, and this is a collision in which the objects stick together and move as one after the collision. And what happens in this situation is actually kinetic energy is lost. Actually, the maximum amount of kinetic energy is lost. All right. So I'll just say that here the maximum amount of kinetic energy is lost, because these objects clearly had kinetic energy too, right? They were moving. They have masses. They have some non-zero velocity. So hopefully I don't have to convince anybody that they also have kinetic energy. And if you had numbers for a problem like this, you could go through and you could calculate just how much kinetic energy was lost, right? Because we could also apply conservation of energy to this collision, or we could try to apply conservation of energy to this collision. So the initial energy would be I'll write this out so everybody can see how this looks, right? And we're assuming that this happens in one dimension, so we don't have to worry about the gravitational potential energy. So the initial kinetic energy would be 1/2 mu squared plus 1/2 big M v squared. That's little v. And the final energy is going to be 1/2, and then we sum their masses, right, times big V squared. And if you had numbers here, you would go through, you would calculate the initial energy, right? You get a numerical value. You calculate the final energy, you get a numerical value, and you would see that these are not the same number, right? In fact, you could make that statement further and say that the final energy is less than the initial energy, right? Because we just asserted that the maximum amount of kinetic energy is lost in a situation like this. Okay, so this is good, and you know, physicists really like to talk about collisions, especially like particle physicists, right? Because I shouldn't say we, I'm not a particle physicist, but like they use, you know, particle colliders, right? And these ideas with, you know, various modifications all still apply in situations like that, where you have these very tiny particles moving at very, very fast speeds. But you know, we're not gonna really get into that at all. But anyway, if we have a perfectly inelastic collision, then like we also might have elastic collisions, right? So I'll just say elastic collisions. And I'll say these are collisions in which both momentum and energy are conserved. Again, let me just fact check myself here, because I want to make sure that this is like the typical. Yeah. Okay, so yeah, this is true. It's not like we have to say perfectly elastic or anything like that. I just want to make sure. So I'll just say that for an elastic collision, then the initial momentum equals the final momentum, and the initial energy equals the final energy. Okay, and I mean I'll make this a vector for momentum. Remember, energy is not a vector, right? But momentum is. So this is what we might have for an elastic collision. And you know, you could go through and you could think about a situation where you have maybe two very rigid objects that collide. Okay, so lots of times when we're talking about elastic collisions, we might think about maybe like pool balls, right? Like the I don't even know if I'm using the right word here, but the cue ball, right? That's the white one, I think. You know, it hits like another ball, and these are solid spheres of a very dense wood, and so you know, very little energy is lost in a situation like that, at least during the collision, right? But you know, like that's very different from a situation in which, you know, energy goes into deforming the shape of the object, right? So you should hopefully have a little bit of an intuition for what, you know, could be like an elastic collision, and what would be like a perfectly inelastic collision. Okay. So maybe one more thing to say. I talked about a perfectly inelastic collision, right, where the objects stick together and move, but you can have just an inelastic collision where maybe they don't stick together and move as one object after the collision, but still energy is lost, and you just kind of have to apply what you know about energy and momentum to figure out maybe how much energy was lost. All right. Okay. So let's look at a couple examples here. I think I've talked about everything I need to talk about. Oh, actually, there's one more thing. And I personally don't care all that much about this, but you will probably need this for the homework. So let's just talk about graphical analysis very fast. You know, much like we could calculate work by looking at a force versus displacement plot, we can calculate impulse by looking at a force versus time plot. Okay, so it's almost the exact same thing, except whereas before we had, you know, a position or displacement on the horizontal axis, now we have a time, right? And everything that I said previously is true for this case also, right? So we conventionally take the area above the horizontal axis to be positive, and the area below the horizontal axis to be negative. Right, so you could calculate the, I mean, we could come back to the picture that I had before, which might have closed it though. I've got it here, hang on. So this is what we were talking about before, right? With work. But now you could imagine that instead of a displacement here on the horizontal axis, we just have a time. Okay, and in that case, it's the same exercise. You just find the area using some basic geometric formulas, and you just have to remember that above the horizontal axis, the area is considered positive, and below it's considered negative. All right, exact same formalism there. So I don't think I'll say anything else really about this, but of course you guys can ask questions if you have any. Okay, let's look at some example problems then. Alright, here's a good one, I think. Although apparently my intuition for what is or isn't a good problem is not great. That was loud. Alright, we'll look at this one. So a child in the boat throws a 6.4 kilogram package out horizontally with a speed of 10 meters per second. Calculate the velocity of the boat immediately after, assuming it was initially at rest. The mass of the child is 26 kilograms and that of the boat is 45 kilograms. Ignore water resistance, whatever that is. Okay. So let's just talk conceptually about what's happening here, right? So initially, the boat and the child are at rest, right? So we have the situation where the momentum, the total momentum of the system actually is 0, which is kind of strange because, you know, the individual momenta are not 0. You know, after the package is thrown. Okay, so let's say, what do we say here? All right, I probably have to use subscripts. I don't like it, but I'm just going to say that the mass of the package. Please stop and hold. I don't know why you're doing this. The mass of the package is 6.4 kilograms. I'm going to zoom out for a second while I copy this down, and then I'll zoom back in. I have a weird monitor. It's got some, you know, like non-standard aspect ratio, so I understand like there are black bars probably above and below as you're watching this. Sorry about that. Okay, so I'll say that the initial speed of the I'll say the initial the final speed of the package. Okay, the final speed, and I'll talk about why I was confusing myself there in a second. Is u, and that's 10 meters per second. And then we'll say the mass of the child, that's mc, is going to be 26 kilograms. And the mass of the boat is 45. Okay, so as I said here, right, we can analyze this in one dimension. This is essentially a one-dimensional problem, right? Because we're just going to think about immediately before the child throws the package and immediately after, right? And, you know, immediately after the package has been thrown, it should, a very good approximation, only have an x component of velocity. Okay, so the initial momentum is 0. So, I mean, I'll just write this. I'll just write p initial equals 0. Simple enough, right? Because, you know, everything's at rest. This child is just chilling in a boat on the water, right? Not moving. Okay. And so let's look at the momentum after. This is going to be, I'll just call it P. Let's just say that this is the momentum of the package plus the momentum of the child plus the momentum of the boat. All right, so everything has momentum after this happens, right? Package is moving to the right, and the child and the boat are moving to the left, and they have to be because you can't just throw this package and expect nothing to happen to the boat and the child, right? So let's write out what this is. Oh, do they tell us to call it V? Okay, I'll just switch this up to make it consistent with their notation. So we'll just say v. I don't like it, but we'll say that. Okay, so the package is moving to the right, so its momentum will just be mv. Okay. The child is moving to the left, so I'll just say that this is negative u, right? So u would be the speed, negative u is how I'm making it a vector and indicating that this is happening in the leftward direction. And then the mass of the boat is also going to be negative u. But, whoa, okay, let me rewind for a second there. The momentum of the boat is also going to depend on negative u. So I wrote the correct thing. I said something wildly inaccurate, but I wrote the correct thing. Okay, so we can simplify this a little bit, right? We can write that this is mv. Maybe we write minus little mc. And I'm really all over the place with my notation here. I should call this big M. I apologize. And this should also be mass of the package. Okay, so that should be good now. All right, I think everything's fine. So we can write it like this. All right, and this is good. So the mass of the package times its speed minus essentially what is the momentum of the child in the boat after the package is thrown. Okay, so let's just knock this out. Then conservation of momentum. Right, and we can apply conservation of momentum here because there are no external forces. The only forces that are being applied are between all the objects that are in our system, right? That's why we can apply conservation of momentum here. So we're just going to say this is 0 initially, right? We agreed that the initial momentum was 0. And I am going to then write the final momentum, which is just this. Okay. And what do we want to solve for? We want to solve for the velocity of the boat. I'm going to solve for the speed of the boat because that's just how I've set myself up to do this. But then you could, afterward, just remind yourself that it's moving to the left. So I think that's hopefully pretty clear. Okay, so then what we want to do is we just want to rearrange this a little bit. I'm going to move the negative term to the other side here. So we just find something like this. And then u should be, I want to write this somewhat suggestively here. This is going to be m of the package divided by m of the child plus m of the boat times v. So notice that here, right, I have a mass over a sum of masses. So this works out to be dimensionless, and this makes sense because, I should find that the answer has dimensions of speed or velocity. And I do, because this is just some pure number, right? And I find that it works out to be that pure number times the speed at which the package was thrown. Okay, so this is a pretty good example, I think, of what conservation of momentum looks like in practice. All right. So let's maybe look at another example here. We can talk about impulse. And there's a problem that I like in the textbook, so I'll just pull that out and we can work through that. And then I think maybe we'll just end with that. I'll trust that you guys, will like work some examples of your own and ask me questions if anything is unclear. Oh, maybe I shouldn't trust you to ask questions. You really hate asking questions. That's okay. I've been in that situation before too. All right, so this is more going to be just a direct computation of impulse here. And what we have is we just have a collision, right? We have a collision of a tennis ball with a wall, and we're told pretty much what the initial momentum is and what the final momentum is, right? Because we're told the speeds and the angles. So good to go. So we just have to figure out what the impulse was, right? And remember, this is the force times the time. So what we're solving for here is the force times the time that the wall exerts on the ball. Okay, let's do that. So I'll just use this as an opportunity to talk a little bit more about momentum. I'm going to first define some things, right? So we'll say that this is the angle is 45 degrees. The mass is 0. I probably don't need to do this because like they tell you in the problem statement, but it's just such a habitual thing at this point that I kind of cannot control myself. So V is 25 meters per second. Okay. So let's talk about what the initial momentum looks like in this situation. So we're thinking about the instant before it hits the wall here. So the initial momentum looks like this. I'll call it P naught. And now we need to actually think about it as a vector. So this is just going to be m vx, m vy. Is that right? Yeah, because it's moving diagonally upwards, so it should have a positive x component and a positive y component, right? So I'll say that this is going to be, we can actually factor out the m, that's perfectly fine. And then I'll just say that this is v cosine theta for the x component and v sine theta for the y component. And if this is not clear to you, just maybe make a sketch for yourself and try to convince yourself that this is what the velocity vector is, okay? So we just take the mass and multiply that by the velocity vector. Good. Maybe I should take a second to convince myself that it's good. Yeah, 45-degree angles are nice because, you know, the other angle is also just 45 degrees, right? So we have this. We have the final momentum. Looks like this. We'll call it P final. We'll just put no subscript on it. And I will write this as, let me be careful here. Let me say mvx prime mvy prime. But you know, these are the same number. One will become negative, right? And I'll just write this out, and then maybe instead of talking about why I'm using this notation, I'll just write it out. So the x component we can see should be negative because now it's moving to the left, right? It's still moving up, so the y component should be positive. So we'll just say v sine theta. Okay, and this should be good. And this is my momentum vector, right? My final momentum vector. So the impulse is, and we'll just call this I. This is just delta p. Not that delta, right? And this is just going to be P final minus P initial. And so we have to be careful here, right? Because we have a minus sign in our final momentum. So, you know, you have to be very careful with all this vector stuff that we've been talking about for, you know, most of the semester at this point. And I mean, again, it's just because impulse is a vector and momentum is a vector, right? So I will actually just double check myself very fast here. Initially, the velocity vector is going to have both components positive, and then finally it will have just the x component negative. Yeah, this is good. So it's just, you know, it's just a matter of writing this. And we should see, or we find, right, that the y component of the momentum just disappears because it's mv sine theta minus mv sine theta, right? So it's really just the x direction. So what we end up having is we have for the x direction it's just negative 2 mv cosine theta, and for the y direction it's 0. And this hopefully makes sense, right? Because as the ball collides with the wall will exert like a normal force, let's say, on the ball, right? And that should be perpendicular to the surface of the wall. And what that means is that this force is exerted directly to the left, which is our negative x direction, right? And that's why we find that the impulse has a negative x component and a 0 y component, right? So you could, in a situation like this, you could maybe even just assume that the impulse should not have a y component because the force that this thing exerts is directed perfectly to the left. But I would suggest that you don't try to take shortcuts until you're sure that you very clearly understand all this stuff. But it is, it is true. And so, I just really wanted to draw your attention to the fact that this, this checks out because it should be a force to the left and it should have no y component. If you knew the time in this situation, you could actually figure out what the force was, or maybe the average force, right? Because typically, forces are not constant, right? More generally, forces are not constant. But if we know the average force, then we're fine, because we can just use the average force to calculate the impulse, and mathematically it works out the same as doing an integral for some some time varying force or whatever, right? And this idea also applies to work actually too. Okay, so this is kind of a crash course on impulse and momentum. Maybe when we reconvene after spring break, I will just talk a little bit more about this. Maybe see if you guys have questions, whatever. But I don't really think we can spend too much more time talking about this, so I'm just going to kind of leave it to you to work out a lot of the details for yourselves, with my help if you need it. And yeah, I think that sounds good. Let's think about, is there anything else I need to talk about? I'm gonna just take a quick look at the homework here before I end the video, because like I've been gone for an hour. It's very much looking like I've covered everything. Okay, so as I'm looking at the homework, the one thing that I'm noticing is that they use a big J for the impulse as opposed to the I, and I think I mentioned that. It's fine. I don't really care what you call it I, call it J, but just use whatever notation is least confusing for you. Okay, yeah, but I think I hit everything that we need to, discuss for this. So let me know if you need any help with the homework. I'll be around the whole break, so I'm not suggesting that you deny yourself spring break, but some of you, for some of you, if you don't have plans, it might be a good time to get caught up on the material, and I'll be here if you need my help with that. Okay. All right. Have a good one. I will see you after the break.